good morning. Today we'll discuss the maximum power transfer theorem. The fourth theorem in your unit number 2 syllabus, the maximum power transfer theorem. In this class we will see the statement of the theorem and also the explanation and also the proof of maximum power transfer theorem. In the last class we have been discussing about determining the Norton's equivalent of a given circuit. In today's class, I hope that by the end of this lecture, you will be able to state and explain maximum power transfer theorem. So I'll start with the statement and then we'll move on to proof and then as usual the key points and finally the applications of maximum power transfer theorem in your daily life. So let me start with the statement of maximum power transfer theorem. I normally call it as MPT theorem, which indicates it is maximum power transfer theorem. It states that in DC circuits exclusively, maximum power can be transferred from source to load only when the load resistance is made equal to the internal resistance of the source. In other words, when RL is equal to internal resistance, then maximum power can be transferred to the load. Internal resistance is nothing but here Thevenin's resistance of the circuit. So that's fine. In other words, it can be stated that maximum power is obtained from a linear circuit at a given pair of terminals when the terminals are loaded by Thevenin's resistance, which means the loaded RL must be equal to your RTH. But you know that Thevenin's resistance is calculated using Thevenin's theorem and it is the equivalent resistance viewed from the load terminals with the load removed and all EMF sources replaced by their internal resistances. So, to repeat again, maximum power can be transferred to the load only when RL is equal to RTH. In that case only, maximum power can be transferred to the load. So, let's see the proof of this particular statement. Now, let us consider there is a very big network, something like this, a very big network, and there is a load resistance here. Now you know that this entire network can be replaced by its Thevenin's equivalent, which is equal to your VTH and this is your RTH, right? So this is your Thevenin's equivalent. So your entire network is being replaced by VTH and RTH. This is what we have learned in our Thevenin's theorem also. So for convenience sake, I am just representing it as V and this one as Ri, which indicates it is the internal resistance of the circuit, or technically it is a Thevenin's resistance. So your entire network is replaced by a voltage source in series with the resistance, and this is your RL. If this is the case, what is the current which is flowing in the circuit? I is equal to VTH by, this is the total voltage, and the total current is RTH plus RL, or you call it as V by Ri plus RL. This is your current which is flowing in the circuit. And what is the power which is transferred to the circuit? So this is the current through load resistance. And if you want the power which is delivered to the load, PL is equal to I square into RL. You know the I value I am getting here. This is V by Ra plus RL whole square into RL. I can write it as V square into RL by R plus RL whole square. This is what your power which is transferred to the load. Now you need to maximize this power which is being transferred to the load. So in this equation, which is equal to PL is equal to V square into RL by R plus RL whole square. Assuming that V and Ri are fixed for the circuit and only RL is being varied. In that case, to obtain the maximum power, what we should do, we should differentiate it with respect to 0. Differentiate it and equal to 0. And with respect to what? The only variable term in this one is RL. When I differentiate this one with respect to RL, I think you know the differentiation, so I am skipping this part. So, yeah, you can go through all this derivation. So finally, what I'll be getting is RL is equal to RL. Right. If you want the derivation, I'll do it for you. So this is V square this is to be made 0, right? So in this case, if I take this one as u by v, you know u by v derivation is nothing but vu dash minus uv dash, right? So, or uv dash minus vu dash, anything is fine. So in that case, v square is constant. So if I take this is v ri plus rl whole square into rl into, if I differentiate this one, I'll get 2 into ra plus rl minus, I'll keep ra plus rl whole square like that, and I'll differentiate it, I'll get it this one. So this is my statement. Now I'm going to expand this one. I'll get 2 RIRL plus 2 RL square, and this term, this is equal to, okay. So now if I subtract, and I'll be getting RL square minus RI square. V cannot be 0, and Ri plus RL also cannot be 0. The sum of two resistances can never be 0 because both will be positive order, at least in DC circuits. So this condition is satisfied only when your RL square minus RI square is equal to 0, which means that RL is equal to RI. So it indicates that maximum power can be transferred to the load only when load resistance is equal to internal resistance of the circuit, which we call it as Thevenin's resistance. Now, key points regarding this particular thing, we have seen that maximum power can be transferred only when RL is equal to RTH. If that is the case, now you know the circuit. This is VTH and this is your RI, or what we call it as an RTH, and this is your RL. So to get maximum power to be transferred to the load, your RL must be equal to your RL, isn't it? In that case, if you carefully see, what is the efficiency of the circuit? This is your output, this is your input, right? This entire is your input. In this entire input, you are taking only this one as output. So what is the output power? Output power is equal to I square into RL. What is the input power? I square Ri plus I square RL. I square Ri plus I square RL. If I take I square common, it is Ra plus RL. You know, for maximum power to be transferred, Ra must be equal to RL. So if I replace this one, I will get 2 RL. Now you see what I am getting 1 by 2, which is nothing but my efficiency is going to be 50% if I let my circuit transfer maximum power. This is an important point to remember. If maximum power is to be transferred to the load, then you will be getting only 50% efficiency. Similarly, the voltage also. The load voltage also will be 50%. You know, the circuit. This is VI, this is this is RL, this is RI, and this is V. So what is the load voltage? VL is equal to I into RL. What is I? V by RL plus RI. So what is VL by V? It is exactly half because both are same, right? For maximum power transfer. So in that case also load voltage. Under maximum power transfer, efficiency is 50% and load voltage is also 50% of your input voltage. This is VTH in 50% of your Thevenin's voltage. And also, now if you say that maximum power transfer, when maximum power is transferred, what is the efficiency? 50%. What is the load resistance or load voltage? It is half of input voltage, or in this case it is VTH. Now what is PL? PL is equal to VL into L, right? So what is this one? VTH by 2 into VTH by RA plus RL. Both refer to same, right? So I'll take it as 2 RI, or I'll take it as 2 RH. 2 RI, or I'll take it as 2 RTH, right? So if you carefully see what is the equation now, this is VTH square by 4 RTH, or in my words here, V square by 4 RI. This is what I have written here. So maximum power which can be transferred is equal to VTH square by 4 RTH. Okay. So these are the important things which you need to remember. Maximum power can be transferred only when RL is equal to RI, and the maximum power which can be transferred is equal to VTH square by 4TH square, 4TH. Okay. And where we actually employ this maximum power transfer theorem? This is a big question because we have been learning so many things. I have told you in the past classes also, when superposition theorem is applied, when Thevenin's theorem can be applied, when Norton's theorem can be applied. Now today we will see how maximum power transfer theorem can be employed by you. So let's take the communication circuits. You know, there might be a mic and there is a person who is speaking with some mic before him, and you are a person whom you are adjusting the sound such that this guy speaks out loud. So this is just like your public address system, right? So here you will be setting your things such that the maximum power will be delivered to the speaker from your amplifier. Here you will be having amplifier, right? And here you will be having a load, what you call it as a speakers. You will be adjusting your amplifier such that your load will get the maximum output. What you will be adjusting here? You will be adjusting your R. You will be adjusting R such that your RL is equal to RTH. Then only your speaker will get the maximum sound. Otherwise, you will be getting so much of disturbance, or you will be getting very low voice. So the person who will be sitting there near the dais, he will be adjusting such that the same resistance will be the same, such that maximum power will be transferred from the amplifier to the speaker. Okay. It may not be possible all the time the human being to adjust the resistance. So what they will use is they will use transformers. Transformer will adjust the impedance. In AC circuits, you will be having impedance, right? Just like your resistance in this case, you will be having impedance. So transformer will adjust that's why it is called as impedance matching. And the transformer which does the job of impedance matching is called as impedance matching transformer. Okay. This is one thing. As a communication engineer, you are from electronics and communication, right? So you should remember this. Impedance matching is one phenomenon. Why impedance matching is done? To extract maximum power. The second application is for a car battery. Whenever you are trying, let us suppose you take a complete winter season. Your car has not been used, so it has been struck. It is not getting started. So what you will be doing? You will be turning on the battery, and you will ensure that maximum power is being drawn by the car from the battery in order to get heated up. If you do it all the things, if you parallelly apply all the things, then your battery will not be supporting your car to get started. So that's why during starting, what we will do is nothing but we will try to match the impedance of the battery, such that your motor which is present in the car, it will completely draw the power from the battery. So that is one case. If you are an electrical engineer, you can easily understand, automobile engineer also. In order to get the maximum power extracted, what you will do, you will try to match the impedance of your motor with that of the battery connection. Okay. So like this, you can find many applications of maximum power transfer theorem in your daily life. So, but as an electrical engineer, I don't prefer maximum power transfer. Why? Because if I try to maximize the power which is to be transferred to the load, then it will be done at 50% efficiency. I don't want my system to be running at 50% efficiency. So that's why I'll do my own modifications. But right now for you, G-level, for you, I think you have understood why maximum power is to be In some cases, you will be required to transfer maximum power to the load, and try to identify those situations which you may be encountering in your daily life. Okay, so that's it from my side, and I hope that now you are able to state and explain the applications of maximum power transfer theorem also. And there is a problem for you. If you carefully see, you need to find the value of the resistor R so that maximum power is transferred to this one. It is very simple. In order to obtain maximum power which is to be transferred, what you need to do, R must be equal to your R Thevenin, which means you should calculate Thevenin's resistance between these two terminals. You have done it in the past 2 weeks, you have been doing the same, so try it again. And to determine maximum power, what you do need, VTH square by 4 RTH. In that case, what additionally you do need? You do need VTH. That is also you have been practicing over the last 2 weeks. So try to solve this problem. All you need to do is nothing but determine VTH and also determine RTH. The same as your Thevenin's and Norton's theorems. Once you get those values, you will easily determine what is the maximum power which can be transferred to the load. Okay, try to solve this. Come back to the class. We will solve some more problems in the class. Thank you.